Chapter 15 is on acids and bases. Chapter 15, Section 1 begins with introducing what an Arrhenius acid is. There's a few different definitions we'll be looking at, and this is just the first. According to Arrhenius, an acid is something that when you dissolve it in water will increase the hydronium ion concentration, or H3O plus concentration. Some basic properties of acids: they have a sour taste, they're going to be conductors of electricity, and when they are combined with metals, they will react to produce hydrogen gas. So you'll see some bubbles coming off usually. We did the splint flame test with those ones before. It made the popping noise. That was your hydrogen gas being produced. An Arrhenius base is a substance that when you dissolve it in water will increase your hydroxide or OH minus concentration. Some properties of bases: they are slippery, kind of feel like you've got soap on your hand that hasn't been completely washed off. They have a bitter taste to them, and they too are electrical conductors. For naming acids, there's two different ways to look at it, and you have to first identify how many elements are present in the formula. If there's only two elements, like HCl, then you would follow this method where you use the hydro prefix and the ic ending. So we would say HCl would be hydrochloric acid. If it's a compound that has three or more elements, then you would follow this method. You don't use the hydro prefix. What you have to pay attention to instead is which polyatomic ion it has in it, so whether it's the 8 ending or the ite ending. If it's got the 8 ending, you're going to change it to an ic, and if it's an ite ending, it becomes an us. So here's some examples. This one has 2 elements, so we add hydro and ic to the ending, so hydrobromic acid. This one here has 3 elements, so we have the carbonate ion here. So the 8 ending becomes ic, and we call it carbonic acid. No hydro prefix when you have more than 2 elements. If it was CO2 with a 2- charge, the carbonite ion, then it would be carbonous acid. This one here, we have H2SO3. SO3 is the sulfite ion, so we say this is sulfurous acid. If this were H2SO4, then this would be sulfuric acid. There's a table in your book of strong and weak acids and bases. A strong acid is something that almost ionizes completely when dissolved in water. So like this one here, nitric, HNO3, adding to water, almost all of this HNO3 will split into its component ions, so the nitrate ions and the H3O plus ions. Weak acids are only going to dissociate partially. So this one here is acetic acid, and you get these to split apart into the hydronium and the acetate ion, but not as many ions. So strong acids ionize almost completely, weak acids do not. The one that you do need to know is that HCl is a strong acid. So hydrochloric is a strong acid. The other ones you can look up in your book. Bases act the same way. The more they dissociate, the stronger they are. So like sodium hydroxide almost fully dissociates, so that is a strong base. This is one that you will need to remember. And then weak bases, only a few of those will dissociate. So like this one is ammonia, and it's not going to dissociate as much, so it will be a weak base. Again, those are a table listed in your book. The only ones you need to have memorized are HCl and NaOH. We just use those ones a lot in the lab. And then the other thing people tend to get confused is that strength does not equal concentration. So an acid or base is strong or weak by how much it dissociates. Concentration is how much that you have dissolved in a particular amount of solution. So you could have 1 molar hydrochloric acid, which is a very dilute solution, but it's still a strong acid. Or you could have 12 molar hydrochloric, which is a very concentrated acid, and is also strong. So strength and concentration are not the same thing. A neutralization reaction is what happens when you combine an acid and a base together. So you get the hydronium ion from the acid combining with the hydroxide ion from the base and produce water. This reaction is called the self-ionization of water, when water breaks into those two ions I just mentioned, the H3O plus of the hydronium and the OH minus of the hydroxide. And we're going to introduce here an equilibrium constant, similar to what we did in chapter 14, but instead of just calling it our regular KEQ, this is specifically for water, so we're going to call it KW. This is the auto-ionization ion constant for water. Now, at standard temperature, hydroxide and hydronium are going to be equal concentrations. They're at 1 times 10 to the negative 7th molar. So if we plug that into our equilibrium expression, Kw is equal to the concentration of our aqueous products multiplied by each other, and you plug those values in, you'll always get Kw as 1 times 10 to the negative 14th. So this is a constant value. You will always have Kw. It will be 1 times 10 to the negative 14th.